Welcome to your next lab. This one's on Newton's second law, and here's the apparatus we're going to use. This is an investigation to see the relationship between net force, mass, and acceleration. So let me show you on paper just a little bit of what we're getting into. If we make a diagram of the equipment, so we have this metal track that the cart's on, and we'll say the mass of the cart is capital M. There's a string attached to it that passes over a low friction pulley, and then hanging from that is a little bag. And we're going to stack up tiny masses in there. We'll say whatever mass is in the bag is some lowercase m. Okay, so the whole idea, Newton's second law, tells us that the sum of all forces is equal to the product of mass and acceleration. So we can say the net force on the entire system is equal to the mass of the entire system times the acceleration. Obviously, if we algebraically rearrange, acceleration should be directly proportional to force and inversely proportional to the overall mass of the system. Now, in any good experiment, we don't want to change two variables at once. So what we're really doing is seeing how is the acceleration affected when we change one or the other of these two things. So we've got to keep one of these constant. And what we'll do is we'll keep the mass of the whole system constant. Even though we're going to add more and more mass into this bag, we'll still be able to keep the mass of the system constant in a tricky way. The masses we're going to be adding to this bag will be coming off of the top of this cart. So if I remove one mass from the cart and put it in the bag, the mass in the whole system has stayed the same. So let's make some force diagrams and see if we can derive another expression based off this idea from Newton's second law. So let's go to the board. Okay, so here's the exact same diagram. Capital M is the mass of the cart, and lowercase m is the mass that's hanging in the bag. So we want to show all the forces that are acting in this case. So let's make a free body diagram. We'll put a little dot as a stunt double to represent this mass. And obviously, gravity is the overwhelming force in this case. So what do we put? Lowercase mg. And it's resisted by the amount of tension that pulls upward in this string. So we're going to draw the upward vector. And clearly, this upward vector should be smaller than the downward vector because gravity is larger in magnitude than the tension, which is why it's going to accelerate downward. However, the tension is the same throughout the entire string, so the very tension that's pulling up on the small mass is the same as the tension that's pulling to the right on the large mass. So we make a free body diagram here as well. And whatever length I made that vector, it's good practice to make it the same length here. And my diagram, I pictured it being on wheels, and in fact, they're very low friction wheels that we're using in this case. So we don't have to draw any resistive force like friction going back in this direction. There is, however, the track pushing upward, so we call that the normal force. There's gravity pulling down, that one would be capital Mg, but we know those wipe each other out. This cart is certainly not going to accelerate on the y-axis. So if we look at the whole system, now we can decide what are internal forces and what are external forces to the system. This force of gravity acting on the small mass is external to the system, but the tension that pulls this to the right and the tension that pulls this one upward are internal to the system. So as far as the net force on the entire system goes, it's strictly just lowercase mg. So if Newton's second law is expressed as acceleration is equal to force divided by mass, I could label this object number 1, and I could label this as object number 2, and it would be correct to say that the acceleration is the net force on object number 1 divided by the mass of object number 1. And just as well, I could say it's the net force on object 2 divided by the mass of object number 2. As long as I'm consistent, the equation is correct. I'm going to choose to be consistent by taking the net force for the whole system, but then being careful to make sure I'm dividing by the mass of the whole system. So if we make our substitutions, the net force on the system is only the external force of lowercase mg, and the mass of the whole system is little m and big M combined, so it's little m plus big M. So let's just factor this out a little bit. In the end result, we should get A is equal to G times the quantity little m over little m plus big M. So this is it. We're going to try to verify that this formula for acceleration is correct. Now, don't make the mistake of thinking this is how we're going to determine acceleration. We're just trying to verify that this equation is true. So you're not going to plug in masses into this equation in an attempt to get acceleration. No, we're going to measure the acceleration by measuring distances and times. So there's going to be a photo gate. And that photo gate sits here, and there's a little object that's attached to the top of the track that has two small marks that are separated by a known distance. I believe that distance is 1 centimeter. If we're careful to set the distance between the item that's attached to the cart and the photo gate at exactly 50 centimeters every time, and knowing how far the cart is released from rest toward this photo gate, if we can use this to measure a final velocity by knowing how quickly those two little marks pass through that gate, well, then we can use kinematics. If we know a distance, an initial velocity of 0, and the photo gate gives us a final velocity, okay, if that's known and that's known, then to solve for acceleration, we just need to use a kinematics equation that doesn't factor time into it, right? So I'll leave it up to you to recall your knowledge of kinematics and figure out what equation is going to work best. But we're going to directly, well, indirectly measure acceleration. But acceleration is a measured quantity, not a calculated quantity when we look at this expression. So that's the gist of the theory behind this lab. So let's go back and take a look at the particular items and possible pitfalls in the experiment before we go on to collecting data. Okay, so let's go back to the actual setup, and we'll take a look at how all of the equipment satisfies the theory of the lab. You notice that there's bearings on the bottom of this cart, and I gave it a flick, and it spins and spins and spins with very little resistance. So there's leveling legs to make sure that there's, no force of gravity along the incline, right? And then this string passes over a very low friction pulley, and at the other end of the string, of course, is that bag we referenced. So I believe the way this is adjusted is the track isn't perfectly level with these legs. We've faked it out. The paperclip and the bag have some mass. So if I incline the track just a little bit, so it's kind of pointed uphill, then the tiny bit of force this way from wanting to roll back hill is canceled out by the amount of tension in the string produced by this mass, and then it's as if we've re-zeroed it, and the mass of the bag and the paperclip now don't affect the system, and I would have to take one of these masses off the cart and put it into the bag for it to begin to accelerate. So everything's zeroed out at this point, and when the bag has none of these masses in it, the acceleration should be 0. So if you look closely here, this is the piece that has the two markings, and when those two markings pass through this photo gate, the first marking initiates a little, there's a beep and an LED goes off, and then the second marking goes through, and essentially it's just measuring time through the smart timer, but then it's like a little computer in here, right? A little calculator, and it takes the distance between those divided by the time that it's sensing, and it actually spits out a velocity. So we put this back on here, and we have to make sure that all the heights are adjusted correctly so that when it passes through, the photo gate is being triggered not by any of the other markings on here, but it's actually that line and that line that line up right with the eye of the photo gate, and it should give us a beep, 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 beep. Okay, so let's plug in our smart timer. Make sure the cord doesn't interfere with the motion. When we turn it on, it's going to ask for what measurement we want. So we select the measurement. We actually want to calculate speed in this case. We select the mode, and it has an option for one gate, collision, pulley, one gate. Yeah, one gate. We're using one photo gate at the end of the motion to get speed. So now if I hit this start-stop button, as always, it doesn't actually start doing anything. It just means that it's armed at that point. So first thing we've got to do is pull this back so that the distance between the photo gate and the distance between the center of those two markings is exactly 50 centimeters. So if you look closely here, the photo gate can be aligned on a convenient marking, and we can put the middle of it right at the 100 centimeter mark on the track, which means all I have to do here is pull the cart back to the 50 centimeter mark. Now, I want to see if you've caught my mistake. Some of you might notice it, right? It's not the leading edge of this cart that passes through the photo gate. That's not what's doing the sensing. It's those two little markings. So this is the point that needs to be 50 centimeters back. So it might be better to move this over to this side of the cart, and then I can eyeball and put that line right at the 50 centimeter mark. Now there we go. Now when it comes to releasing this from a state of rest, I could put my fingers here, but you might make the mistake when you let it go of giving it just a little bit of a forward push. So I find it works a little better if you just take one finger and set it there to hold it at rest. And then when it's time to go, you just pull that finger away. Now, of course, it shouldn't be going right now because the force should be 0, right? We've negated the mass of the bag. So all we have to do now is have my lab partner put one of these masses in the bag. I put my finger here, and when it's time to say ready, set, go, after my partner has put that mass in the bag, they're just going to hit the start-stop button. You'll hear a beep. The asterisk will show up on the screen, and when I release my finger and the photo gate senses that this object has passed through, it'll just spit out some speed. I believe it's measured in centimeters per second, and we can record that velocity. So let's move on to data collection. All right, time to start collecting some data. And just to remind you again, each one of these 10 little masses that's coming off of the cart and into the bag, and therefore remaining in the system, is taken to be exactly 20 grams. So you're going to have 10 data points, 20 grams in the bag, 40 grams in the bag, 60 grams in the bag, and so on until we have all 200 grams in the bag. And then each time I get a speed, then I'll just bring this closer to the camera and you can zoom in and you can build your own data table yourself from there. So first data point, 20 grams in the bag. Make sure we've got the distance of 50 centimeters. I hit the start-stop button, and that doesn't actually mean start, it just means it's armed. At that point, we can release it. And I'll let you take a look. This is a measurement of centimeters per second. So you've got a mass versus a speed. Next data point, an additional 20 grams in the bag, so now a total of 40. Every time I hit start stop, my partner has time to wait for a moment, but he can release it at any point after that. So I've hit the button, and there we go. No surprise, with more mass, we have greater speed as it passes through the photo gate. Third data point. You can start not only releasing it, but then also, if you want, catching it, just as long as your hand doesn't hit the cart before it's all the way through, so stuff doesn't slam. There you go, third velocity measurement. On to data point number 4. 4 20-gram masses are now in the bag. Photo gate is armed. And here's our velocity. Data point number 5. Data point number 6 coming up. Getting dangerous. Okay. We're getting close. We're at number 7. Woo! Now we're trucking. Okay, here comes number 8. All right. Got it? 2 to go. 9 20-gram masses in the bag. Photo gate is armed. Okay. Here's another value for you. And on to the last one, 10 out of 10. Arm the photo gate. And there we go. So you have 10 different masses and 10 different speeds. Using kinematics, you can convert these speeds into an acceleration using the correct kinematics formula. And so in the end, what you really have is a set of data for acceleration versus the net force. And when you make a graph, everything should come out just fine.